Okay, welcome everybody. It's a pretty exciting day. It's Bastille Day, 14th of July. But in February 1985, this department came perilously close to abandoning its traditional emphasis on synoptic dynamic meteorology. But a burst of impassioned correspondence from alumni ranging from line forecasters to Louis Uccellini, who was then the director of the mesoscale analysis and modeling section at Goddard, convinced the department to spare the program. And this crisis occurred in the exact same week as the Hoskins, McIntyre, and Robertson paper that reintroduced the community to potential vorticity and greatly reinvigorated consideration of PB as a means to consider the cyclone life cycle. And thus began a remarkable revolution in our subdiscipline, some of which you'll see on display today. And so on this Bastille Day, the anniversary of a famously failed revolution, it's my great pleasure to introduce today's speaker, Mr. Patrick Beaty. Patrick is a Madison native, but for reasons that are probably best left for discussion on another occasion, he did his undergraduate work in meteorology and climate at the University of Nebraska-Lincoln, where he also took a minor in math and physics, and where they used to have a football team. Of course, Patrick excelled at UNL, and having done undergraduate research there on forecasting mid-latitude winter cyclones, he found the work that Michael and I were then engaged in to be of interest and applied to graduate school, looking to earn his master's degree and then join the Weather Service. So he joined my group in September 2019, and within a couple of months, the event that he'll describe to you in just a minute occurred and set him on his research path. And you know, it's always fun to look back at a student's application as they approach graduation, because by then you've come to know them pretty well, as compared to the time of application when you're trying your best to get some sort of sense of what the future might be like based only on what's written on paper in front of you. In Patrick's letter of intent, he mentioned 3 characteristics that he thought best described him: a strong work ethic and ability to finish tasks on time, check; organizational skills, check; and lastly, persistence. And let me tell you, he was right about all of them, but boy, did that last one come in handy here at Wisconsin, because the key analysis tool at the center of the work he's going to discuss today, the piecewise PV inversion code, is pretty complicated, and it took quite a while for him to get it working in the way that we were confident it was doing it right. But it was well worth that time, as it's afforded, I think, some interesting new insights into mid-latitude cyclogenesis based on the evaluation of this case. In one of the letters of recommendation that we received with Patrick's application, Professor Matthew Vandenbroek noted that, quote, that Patrick, quote, does a good job explaining meteorological concepts, which makes me think he may be a good candidate for TA position, unquote. That was remarkably prescient. As many of you know, Patrick was who's TA'd at least 5 times. Am I wrong? Is it more than that?
Like 8 or 9. Yeah.
8 or 9, so yeah. I got more than half of it, right? 4 times for me in 452, but he recently won a campus-wide TA award, so that was prescient advice from Matthew. Some of you do not know that while Michael was away at NOAA, Patrick became my trusted partner in crime, delivering our weekly weather watch, regularly introducing those fortunate enough to attend to a host of really excellent resources that he had discovered along the way in his preparation for the discussion. The whole department is going to miss those outstanding presentations for sure. I won't miss losing to him at tennis, hearing about the Twins or the Vikings, or providing hopelessly ineffective counseling as he tries to exercise his allegiance from Nebraska sports. But I will miss his generous and creative sense of humor, his diligence and colleagueship, his excellence in the classroom, and the proximity of the friendship that we've enjoyed, which I expect will continue just in a form that we have fortunately not yet had to explore. And upon successful completion of his degree requirements, Patrick will be off to Daytona Beach, Florida. I'm sure he'll have lots of friends in the next couple of years, where he's earned a 2-year postdoc that will involve both teaching and research at Embry-Riddle Aeronautical University. So today, Patrick's going to share with us his diagnosis of an unusual case of rapid cyclogenesis in the northeast Pacific Basin. Patrick.
Thank you so much, John. Is the mic on? Can everyone hear me? Okay, sounds good. I will, before I get started, I do have to say Nebraska might not have a football team, but we have a volleyball team.
That's true.
And that's the last comment I'm going to make about that. So as the title suggests here, we're dealing with an unusual case of rapid cyclogenesis, but before we get into why this case was so unusual, we're going to talk about the synoptic conditions so we get a sense of how it formed. So we're starting off in late November 2019. This is 12 BTC, 25 November. Here's a surface map. We have a cutoff cyclone sitting to the south of the Aleutian Islands, a large anticyclone over much of the northeast Pacific Basin. There's a baroclinic zone that connects the two, as represented by the 950 theta E. And in between those two cyclones, we have a development region as denoted by the X there. If we go up to 850 millibars, you'll see the same baroclinicity represented closer to the surface, and we have strong horizontal frontogenesis, and it's localized, and it's directly downstream of where our development region is located. Stepping now to the mid-troposphere, 500 millibars, you'll see we have largely zonal flow at this time. So we have a lower level wave, not an upper level wave at this time. 12 hours further, now we're at 0 UTC, 26 November, our cyclone is beginning to develop. It's a 1018 low. It is cutting in between the anticyclone that was originally sitting over the northeast Pacific Basin. You can see still moving along that baroclinic zone. At 850 millibars, we still have the baroclinicity represented and still strong horizontal localized frontogenesis, still ahead of our cyclone's motion. And at 500 millibars, now we see the development of an upper level wave, moving close in proximity but weak at this time. Another 12 hours, our cyclone has now continued to deepen. It's now 1001, 17 millibars in 12 hours. Still moving along the baroclinic zone, that still is stretching in between the anticyclone and cutoff cyclone. And now it's making approach towards the west coast of the United States. We now see a thermal ridge beginning to develop with strong localized frontogenesis directly ahead of our cyclone's motion. And we see now a more robust upper level wave with a strong vorticity strip and vortex gradient right where we have strong horizontal baroclinicity as represented by thickness. So we have very strong cyclonic vorticity represented by the thermal wind, really strong development going on at this time. Last time we're going to look at, now we're at 0 UTC, 27 November 2019. Our storm is making landfall on the west coast of the United States. Deepened 30 millibars in the past 12 hours. The baroclinicity has largely fallen apart. We still have strong horizontal frontogenesis, likely due to the mountains over the Oregon and California coasts. And we have now a very significant, well-developed upper level trough. Very nice ball of vorticity right over our cyclone and stretches well up to the west of the trough here. So this 2019 bomb cyclone largely existed for a 24-hour period from 26 November to 27 November 2019. On the right there is a visible satellite animation you'll see. This storm, the mean sea level pressure dropped 49 millibars in 24 hours. That denotes it as a bomb cyclone or a rapidly deepening cyclone. This included a 1 hour mean sea level pressure fall of 6 hectopascal, which is included in this loop. You can see very nice, very pretty cyclone. This storm set the all-time low pressure record in the state of California, all-time low pressure record, and 2 pressure records for November for 2 cities on the west coast of the United States. So a record-setting storm, a very significant development in late November 2019. Although it was record-setting, that is not particularly why it's so unusual. This storm was unusual, first because it had an equatorward storm track. If we track explosive cyclones over the northeast Pacific Basin in the dashed black lines from a climatology in 2017, you'll see all of them move southwest to northeast or have some poleward component to their motion. Our storm in 2019 moved zonally, then moved equatorward, and then moved zonally again, so entirely equatorward motion. And this is different from the typical cyclones move poleward, anticyclones move equatorward. This storm, also if you plot 2 climatologies of bomb cyclones in this region here and rank them compared to other bomb cyclones, it ranks in the 90th plus percentiles of these 2 climatologies. So compared to all bomb cyclones, we have a 90th plus percentile storm, a very high-end development here. The third reason it was so unusual is because it underwent its maximum deepening location the furthest east of 39 consecutive years. We saw in the previous slide that that was that 6 hectopascal in 1 hour. That occurred at this star here, right there. And you'll see 3 frequency contours of 3 different climatologies that looked at maximum deepening locations, where the storm underwent its maximum deepening. All 3 of those are not as further east as where our storm underwent its maximum deepening. On top of that, it cut through an anticyclone, didn't seem to care about the anticyclone, and it underwent its maximum deepening over colder waters off the California coast. And so these all make this storm so unusual in its development. We saw from the synoptic overview that this storm was a lower level wave before it was an upper level wave. That lower level wave, as it moved along the baroclinic zone, there was a nice cloud head persistent above the lower level wave, and it was driven by lower level frontogenesis, is what's known as a diabatic Rossby wave. Diabatic Rossby waves are a low level positive PV anomaly. They have cyclonic flow around the PV anomaly, and they move along the baroclinic zone here, ZB. As they move along the baroclinic zone, you have meridional heat flux on the flanks due to that cyclonic motion. And if you have positive differential meridional heat flux, you can generate rising motion, W there. That rising motion will develop a cloud head, will get latent heat release, and that latent heat release will generate a positive PV tendency downstream of the initial anomaly. That self-propagates the lower level diabatic Rossby wave downstream along the baroclinic zone through which it formed here. These diabatic Rossby waves are like the classic Rossby wave in that they involve a meridional advection of some quantity to self-propagate. Diabatic Rossby waves are that heat flux component, sometimes moisture as well, which forces rising motion if it's differential, latent heat release, and increasing the PV tendency downstream. Whereas Rossby waves involve the meridional advection of the background poleward to equatorward PV gradient. So they're similar, but this involves lower level heat flux. And as the name suggests, diabatic Rossby waves are diabatic in nature. Rossby wave motion is adiabatic in nature here. And so we're interested in the interaction between this diabatic Rossby wave and the upper level trough that eventually took shape and moved over our cyclone here. There have been a lot of studies that have looked at the interaction of these two waves to force rapid cyclogenesis, and we're interested in this development, particularly because the diabatic Rossby wave preceded the upper level trough in existence here. How we're going to look at this interaction is we're going to use what's called PV inversion or potential vorticity inversion. Potential vorticity inversion involves taking a distribution of PV somewhere in the atmosphere, applying an inversion operator, and backing out a lot of information about that PV distribution within your atmosphere. So let's start out with a positive PV anomaly somewhere in our domain here. We know from Ertel's PV equation, which is in the upper right, that this positive PV anomaly is going to be a local maximum vorticity. The X meaning into the page, the circle meaning out of the page, so that's cyclonic motion. This local maximum vorticity is going to decrease away from the level of the initial anomaly, so it's going to be within some depth of our atmosphere here. If we assume that we are near the tropopause, and this PV anomaly is associated with a dip in the tropopause, we can then conclude we should have a cold anomaly below, a warm anomaly aloft, due to thermal wind balance assumption, which is great for synoptic scale motion. And because we have this distribution of temperature, warm anomaly aloft, cold below, the isotropes should be oriented as such. This also dictates that our PV anomaly is a local maximum in static stability, the spacing between these isotropes and the vertical, due to Ertel's PV equation, and we see that there as well. If we then apply our inversion operation, we can also back out the geopotential height distribution associated with this PV anomaly, which might look something like this. And all of this information about these PV anomalies, we back out from applying the PV inversion operation here. Because we have the geopotential distribution, we can get the geostrophic winds, we have the vorticity, so we can get the U and V winds, and we also have a distribution of temperature with height or thickness. We can back out the temperature and thermal wind. All of this information is within the distribution of PV. It is also true, though, we could have this PV anomaly within the center of a domain. We could also have PV anomalies on the flanks. They don't all need to be positive, some of them can be negative. These negative PV anomalies, if we assume this is our train of PV anomaly waves, will also have a distribution of thermal and wind fields surrounding them. All of this information is included within these PV anomalies, and we back out all that information by doing PV inversion. We can take this operation one step further, because right now we're just saying we're taking PV anomalies within the atmosphere, inverting them, and getting these characteristics out. But what if we want to know what formed these PV anomalies? What were the processes or structures which led to their genesis? And if we want to do that, we can take PV anomalies associated with specific processes or structures and get the information, and then we have a more focused answer, what was causing these thermal and wind fields to exist within our atmosphere here. We do that by doing what's called piecewise PV inversion. Piecewise because you're taking pieces of the total PV, splitting them up, and separately inverting them to get all those wind and thermal fields out of the distribution. For this operation, we're using the hourly ERA5 data, and you'll see we have three types of PV, PV updraft, PV surface, and PV interior here. These all represent specific, unique processes or structures which led to these PV anomalies within our atmosphere. So specifically, PV updraft is dry upper tropospheric, lower stratospheric PV anomalies. These are PV anomalies associated with dry upper level waves, upper fronts, or upper level trough specifically. We can also have PV surface, which is near surface, lower tropospheric thermal anomalies. And then we also have PV interior, which is PV generation from latent heat release. This is our diabatic Rossby component to this development here. All of these are bound by unique isobaric and relative humidity criteria, so there's no overlap. These are all unique PV anomalies, only counted once as we do this inversion. And when we go through and actually separate and make this piecewise, this is what it looks like with real data here, where we take a cross-section. These solid blue contours are positive updraft PV anomalies here, and the dashed orange are negative surface anomalies here. Each of these different PV anomalies, negative or positive, have that characteristic thermal or wind field associated with them. So we do this piecewise PV inversion, and we get information about these processes and structures which lead to our cyclogenesis event. The first way we're going to analyze the results here is we're going to use the 950 hectopascal height tendencies, or the change in the geopotential height, as denoted by the dashed contours up there, to investigate surface cyclogenesis. What we're doing is we're tracking the center of our storm and seeing what was the height change between two time periods. If that height change was negative, that represents an evacuation of mass, a stronger cyclonic vorticity, and a stronger cyclone at a later time. And so we want to know what specifically is doing the surface cyclogenesis for this event, what type of the PV is doing that surface cyclogenesis. We use the 950 height tendencies to do that. First, what we're going to do, we were talking about PV anomalies in the earlier slides. We're going to calculate a PV full perturbation, which is PV just associated with our storm, subtracted by the 2-month mean PV field. So we're isolating PV anomalies just with this storm specifically, getting all the mean field out. When we do that and we do the piecewise PV inversion, we get a height tendency distribution like such in the blue points here. If we compare that to the total ERA5 data, just untouched at the center of our storm, you'll see we're capturing very well the magnitude and the fluctuations of these height tendencies at the center of our storm. So we can trust our results and go forward with further piecewise PV inversion because we're capturing the development here very well. So if we split up these height tendencies then into the three different pieces of a PV, first we can look at the surface PV. These are near surface thermal anomalies. They're resulting in the most cyclogenesis right near the beginning of our storm. You can see then there's a period where it's largely near zero surface cyclogenesis, and then there's a part where it's actually leading to height rises toward the end of the storm life cycle. Next, if we track the height tendencies due to our interior PV, this is our PV associated with diabatic heating, you'll see there's a large period where we have negative height tendencies associated with this diabatically induced PV. So a lot of the surface cyclogenesis during the development phase was forced by our diabatic Rossby, diabatic PV associated with latent heat release. The last bit of cyclogenesis at the surface was due to the upper tropospheric PV here, associated with the upper level wave and an upper front that comes through. So looking at these three distributions here, there's two ones that stick out, specifically the diabatically induced PV and the upper tropospheric PV. So we can conclude then from doing this piecewise PV inversion analysis of the height tendencies that our surface cyclogenesis event was driven by first the diabatic Rossby for much of the life cycle. That's that diabatic Rossby or diabatically induced PV, and then the upper front immediately prior to landfall. So there are two main features that resulted in our surface cyclogenesis. Because we know from the synoptic overview that the diabatic Rossby preceded the upper front in its existence, we can then ask the question, did the diabatic Rossby have any effect in encouraging the development of the upper front? So did these two structures interact? To what degree did they interact during this development? Because we had the diabatic Rossby first and then the upper front second. We do this, we can answer this question by using the balanced wind and thermal anomalies from our PV inversion in the upper right to investigate upper front intensification. So again, we're using the hourly ERA5 data because we have three types of PV, and we have three types of geostrophic wind or wind anomalies, and then three types of thermal anomalies as well. But remember, we took the full perturbation PV and did that inversion. We also have to include the effect of the mean, the background flow field, because that could also result in any combination of this omega here. The omega represents vertical motion within our atmosphere, and any interaction between these geostrophic winds and the thermal fields could result in vertical motion in our case. We are interested in this vertical motion because if we have subsidence through the jet core, we would intensify our upper fronts, and that's what we're interested in answering this question. Did the interior PV do any of that upper front intensification during this cyclone here? So let's take an example of what one of these might look like, because there's 16 of them. We'll pick the interior geostrophic winds acting on the upper tropospheric thermal field in this case. Here's what it looks like from a schematic view, where if we have a PV, a positive PV anomaly associated with the upper tropospheric PV, here's the distribution of the thermal field, and an interior PV anomaly associated with the interior diabatically generated PV. The interaction between the thermal field of the upper tropospheric piece and the interior field of the interior PV piece, that's going to result in vertical motion, and we're interested in this vertical motion that results from this interaction here. And remember, there's 16 different combinations that we could have for this development. Now, if we look at just the upper front intensification from a plan view, what we can see tracking the evolution from 0 UTC 26 November to 18 UTC 26 November, we see there's a coincidence between the geostrophic vorticity at 500 and the baroclinicity as represented by the shading. This is a surefire sign that we have an upper front intensification during this evolution here. And so what we're interested in now is we can pick one of these times and look at the upper front and see what's resulting in its intensification at that time. So let's pick a time early on in the storm life cycle, 6 UTC 26 November 2019 here. We cut this cross section through our upper fronts. Here's what we get. We have a PV undulation as noted by the blue contour here. Directly underneath the jet core, we have strong horizontal baroclinicity, and we have sinking motion as noted by the dark gray contours here. So we have a robust upper front forming at this time here. This sinking motion, this subsidence, or omega positive, is differential though. We have really strong subsidence directly below the jet core, and it weakens to the north. We want to relate this subsidence through the jet core and the upper front intensification to those three pieces of the PV, and see if the diabatic rest wave is resulting in any of this differential subsidence. This differential subsidence is going to tilt the isotropes. That tilting, the isotropes are the red contours here, that tilting is going to result in positive frontogenesis and an increase in the strength of the baroclinicity, like such here. So anywhere in the blue is experiencing that tilting frontogenesis and an increase in the temperature gradient. It is also true, though, that this differential substance is going to tilt the background westerly shear. That tilting of the background westerly shear is also going to result in an increase in the vorticity here, like such, contoured in red. And like any front, an increase in the baroclinicity and the geostrophic vorticity is going to result in an increase in the strength of that front. So what we can do now is we can take this distribution and split up the specific frontogenesis via tilting and geostrophic vorticity generation via tilting. Those we can split them up between the different pieces of the PV and see what's doing this increase in baroclinicity and vorticity at this time here. So we're associating the total frontogenetic tilting with the different pieces of the PV. When we do this partitioning and calculate the tilting frontogenesis, we have the three leading combinations that result in the most frontogenetic tilting at this time. The maximum one I have noted by the star here is omega sub UU, which is the upper tropospheric winds acting on the upper tropospheric thermal field, and omega sub UM, upper tropospheric winds acting on the mean temperature field. So the upper tropospheric PV is doing a majority of the frontogenetic tilting, increase in the baroclinicity at this time. If we go through now and also associate the different, the vorticity generation to the different pieces of the PV, we also see that that upper tropospheric piece is doing a majority of the geostrophic tilting at this time. This means then, at this early time in the storm life cycle, the upper tropospheric PV is dominating the intensification of the upper front. Why we care about this is because if we increase the strength of our upper front, we're going to increase the vorticity gradient, the thermal wind, we're going to have more encouragement for synoptic scale vertical motion via the cyclic development theorem, and we have a stronger storm later on. So we care about what's doing this upper front intensification to see which process is leading to a stronger storm at later times in our development here. At this early time, it's the upper tropospheric PVs doing the most upper front intensification. Now we can pick a time later on in the storm life cycle. We have a much more robust upper front at this time, 18 UTC 26 November. We'll do the same sort of cross-section analysis. We see much stronger differential substance directly below the jet core, which means we have stronger frontogenetic tilting and stronger vorticity generation at this later time. Again, splitting up the frontogenetic tilting and the geostrophic vorticity generation into those different PV pieces, we can see at this time, again, the upper tropospheric winds acting on the upper tropospheric thermal field and upper tropospheric winds acting on the mean thermal field are doing that majority of the upper front baroclinic generation and also a majority of the upper front geostrophic vorticity generation at this time. This is true for every single time throughout this upper front intensification period. The upper tropospheric PV is doing a majority of the upper tropospheric front intensification. So what we can conclude then from this analysis is during the upper front intensification period, the upper front and diabatic cross wave both intensified, but largely did so independent of each other. There was no real encouragement from the diabatic cross wave to increase or to strengthen the upper front during this entire intensification period. This is interesting because other studies that have looked at this interaction to result in rapid cyclogenesis have noted that the diabatic cross wave or the lower level wave has encouraged the development of the upper level wave. In this case, this was not the case. This did not happen. Both intensified largely independent of each other. So now we might want to ask the question then, what were some of the factors that led to the storm being so strong? And we can do that by using ensemble forecasts. So we're going to use then ensemble-based sensitivity analysis to investigate influences on storm intensity. We're using different ensemble number forecasts of the same storm. We have 50 different, we're using ERA5 50-member ensemble data simulations. So we have 50 different ensemble member forecasts which provide 50 different types of simulations of the storm. We can then associate which ones made this storm strong, which one made them weak, and then compare the strong ones to the weak ones and see what was different about those simulations of this storm to see, does that give us any indication on why this storm was so strong? How we do this actual calculation is we calculate a lagged linear regression between a forecast metric. In this case, we're choosing storm intensity within this blue box here off the California-Oregon coast. You'll note this is where a storm made landfall, and this is where it was the strongest. And we're going to correlate the forecast metric to any number of these model forecast states here. In this case, we want to pick specifically model forecast states which are appropriate to our development. We're choosing the 850 frontogenesis to represent the diabatic cross wave, the lower level wave, and 500 hectopascal heights to represent the upper level wave, in this case here. This is lagged in time because we are choosing the storm intensity when it was at its peak to an earlier time to see at an earlier time what did the ensemble see that made the storm so strong later on. And so that's that lagged, that sub-T component here. What we get if we do this calculation is we get a correlation field between the forecast metric and the model forecast state. This one is specifically showing the correlation between storm intensity and 500 millibar heights for our storm here. You'll see there's a large portion right over our cyclone at this time that is has positive correlation in this case here. This means then we have positive correlation between the 500 millibar heights and storm intensity within our blue box, which means if we were to increase the 500 millibar heights in this region, we would increase mean sea level pressure within our box. Said another way, if we increase the heights in this region, we weaken our storm because a higher mean sea level pressure is going to be a weaker storm. This makes sense This is our upper level wave, the beginnings of it. So if we weaken the upper level wave, we're going to have a weaker storm 24 hours later. So these results are consistent with what we are seeing here. We can take this analysis one step further and calculate what's called the sensitivity pattern. This is done by taking the lagged linear regression that we calculate early on, multiplying it by the standard deviation of any of our model forecast states, and taking the average over all ensemble members used, which is capital N in this case. We do this because you'll see now we have the actual mean civil pressure change when we were to increase 500 millibar heights by some amount. And so this gives us now the actual change in the storm intensity when we do this increase or decrease of the heights here. Comparing these two calculations, the same correlation field, as denoted by this yellow outline box, can have a varying sensitivity pattern. So increasing 500 millibar heights within this region that has the same correlation does not have the same change in the storm intensity 24 hours later. So we do this extra calculation because we get more information about, first, what the actual change in the mean civil pressure is going to be, and then we know we have different varying patterns, not just the correlation field in this case. And so what this is telling us is if we were to increase the 500 millibar heights within this yellow region by 1 standard deviation, about 250 meters, we get a varying change in mean civil pressure between 0.4 and about 2 hectopascal increase in the mean civil pressure 24 hours later within the storm here. These sensitivity fields are calculated using all 50 of our ERA 5 ensemble members. When we track the ERA 5 ensemble member storm intensity forecast within this blue box, we get a distribution like such, where there's varying intensities of the mean civil pressure forecast within our box there. Because we're interested in what made this storm particularly intense, we can subset all 50 of these ensemble members to just look at the top 5 strongest depictions of our storm, or the lowest mean civil pressure, in this case, noted by the red dots. So we're particularly going to focus on the average of these 5 ensemble members compared to everything else to see what made these depictions stronger than the other ones. Does that give us any insight into why our storm was strong, particularly in these forecasts of the storm here? So now we go through and we calculate the sensitivity patterns. We're going to use relative vorticity at 500 millibars and 850 hectopascal frontogenesis. This is the upper level wave, this is the lower level wave in this case. And here's the sensitivity fields we get when doing that calculation. And so first, looking at the relative vorticity field, the black contours in both of these represent the ensemble mean. And if we were to increase the vorticity to the west of the ensemble mean and to the southwest of the ensemble mean, you'll see we decrease our mean civil pressure by upwards of 2 hectopascal. This represents, if we were to increase the vorticity in this region, we increase the strength of our storm by upwards of 2 hectopascal. So a negative sensitivity where we have these purple contours here. If we look at the lower level wave, we see we have, if we increase the frontogenesis to the east of where we have our ensemble mean maximum frontogenesis, we also increase the strength of our storm, decrease the mean civil pressure by upwards of 0.8 hectopascal. So now we can take these sensitivity fields and specifically highlight the top 5 strongest ensemble member forecasts of our storm. So if we plot the ensemble, or the anomalies of those top 5 ensemble member forecasts compared to the ensemble mean, what you'll see now, and they're denoted by lowest, meaning lowest mean civil pressure, strongest forecast. What you'll see is we have these top 5 strongest ensemble member forecasts are forecasting an increase in the vorticity to the west of the ensemble mean and slightly to the southwest. This is exactly what we see. If we want to increase the strength of our storm, we want to increase vorticity in this region. That's what those are picking up on. Again, looking at the lower level wave now, we see an increase in the frontogenesis to the east of the ensemble mean maximum. This is exactly where we also have negative sensitivity, or if we increase the frontogenesis in this region, we increase the strength of our storm, decrease mean civil pressure. What this is suggesting then is these top 5 ensemble member forecasts are forecasting a westward shift in the upper level wave. If we move this ensemble mean maximum to the west, we increase the vorticity in that region. And if we shift this ensemble mean maximum frontogenesis to the east, we also increase the frontogenesis in that region. So we have a westward shift upper level wave, a eastward shift lower level wave in this case. What this is saying then is if we want a stronger November 2019 storm in these ensemble member forecasts, we want a later interaction between the upper level and lower level wave. We have our upper level wave, our lower level wave, we're shifting them. We increase the distance between the two, which means there's more time for both of them to strengthen by themselves before interacting with our development here. Doesn't this sound exactly like the QG diagnostic, where the upper and lower level wave are strengthening completely independently? We saw that in the previous section to result in this rapid cyclogenesis event. The ensemble members forecasting a stronger storm are also picking up on this independent intensification during this event here. Now, stepping forward, the ensemble member forecasts are valid every daily, so we have once a day forecast, valid for all 50 of our ensemble member forecasts, so we step forward a day in our storm life cycle. Now we're at 0 UTC 27 November. You'll see this is right where our storm is near peak intensity. The sensitivities have increased right over our storm. We're looking at the relative vorticity field. If we increase relative vorticity right over our storm and slightly to the west of this tail of vorticity, associated with the upper front, we increase the strength of our storm by 3 or 4 hectopascal in this case. Looking at the 850 millibar frontogenesis, if we increase the frontogenesis to the north of our storm, we also increase the strength of our storm, decrease mean level pressure by 3 or 4 hectopascal in this case here. Now if we again plot the top 5 strongest ensemble member forecasts, you'll see we have that exactly where we have a negative sensitivity. In both of these cases, we have an increase in both the vorticity and the frontogenesis, and reflected in those top 5 ensemble member forecasts. So what this is suggesting then is the top 5 ensemble member forecasts are suggesting a northward expansion of this ball of vorticity. So it's stronger where we have that ensemble mean maximum, and shifting this tail of vorticity associated with the upper front to the west. This would lead to an increase in the strength of our storm. It's also suggesting if we shift the lower level frontogenesis to the north, we also increase the strength of our storm in this case here. What this is saying at this later time in the storm life cycle is that a stronger November 2019 storm, we should have a westward tilt with height. We are moving the upper front and this upper level wave slightly to the west and separating it from the lower level wave, which means we have more potential for cyclogenesis, more cyclonic vorticity of action by the favorable winds, even at this later stage of the life cycle of our storm here. And this is what the top 5 strongest ensemble member forecasts are suggesting. So going to the results of the ensemble-based sensitivity analysis, we note that the strength of the November 2019 storm forecasts are dependent on the timing of the upper and lower level wave. We saw that as hinted at by the ensemble anomaly fields and the sensitivity, with specifically the upper level trough and the lower level diabatic rest wave. These are also suggesting that ensemble member forecasts that forecast a stronger November 2019 storm seem to suggest a later upper front and diabatic rest wave interaction, and then independent intensification between the two, which is consistent with what we saw when doing that wind and thermal anomaly analysis here. This is suggesting then that these two features, the upper level wave and the lower level wave, were independently strong. They came together by some luck and resulted in this rapid cyclogenesis event. There was no real interaction between each of these features for this specific event. And this is different because other analyses that have looked at this interaction resulting in rapid cyclogenesis found that there was actually more robust and systematic interaction between these two features here. So after all of this analysis, there's still some ways we can go forward with looking at this specific storm and then also just diabatic rest wave cyclogenesis in general here. So future work, one question you could ask is, was the November 2018 storm the strongest it could have possibly been? One way you can do this is you can use another way to look at storm sensitivity using the Whorf adjoint model, and you can get what's called optimal perturbations, work being done by Brett Hoover and collaborators, where you take forecasts and simulations of the November 2019 storm, or any storm, you can find where you need to make perturbations in the initial conditions to make the strongest storm 24 or 36 hours later. And then you could compare that optimal simulation to the actual storm and see, was it as strong as it could have been? Were there some areas where potentially the storm could have been stronger? Or compare the two, in this case, to see how strong the storm could have been. We're also doing work to compare this storm to a case of cyclogenesis in 2024. These storms were both dynamically similar. Both occurred, this is the 2024 storm on the right there. Both of these storms occurred in the same region of the world, in the Northeast Pacific Basin. Both were diabatic rise waves initially. Both had an upper level wave move over the diabatic rise wave. Both were record-setting storms. Both were explosively deepening. We can use all the tools we have now perfected within this study to compare them and see, were they similar, were they different, how similar, how different were they? There we go. The last question you could ask is, how are diabatic rise waves going to evolve within a warming climate? So we know the climate's warming. We can use a climate model in different scenarios of warming and see how might diabatic rise waves look 100 or 200 years in the future. Is there going to be an increase in strength of these diabatic rise waves? Will they increase in their frequency? Are there different locations on the globe where they'll be more common or less common than they are now? If we have more diabatic rise waves, if they are stronger, is there going to be more systematic interaction between an upper level wave and these diabatic rise waves to result in rapid cyclogenesis? Because these are such highly impactful storms, we want to know how might these look down the road here. We can do that using any of these climate models simulations here. Before I conclude, there are several people I have to thank. First, my advisor, Dr. Jonathan Martin. He has given me every opportunity I could have imagined, and then some, all the experiences, all the criticism, all of the encouragement I will not take for granted and take going forward here. So I'm really thankful for this opportunity to be here presenting in front of you all today. I would like to acknowledge my committee members, Stephanie Henderson, Brett Hoover, Andre Lopez-Lang, Liz Maroon, and Andrew Winters, for not only giving me individual feedback from all of this analysis, but also being great examples of scientists, educators, and people, and I'll take all of your great examples going forward throughout my entire career, I'm sure. I want to thank Michael Morgan and Angela Rao. I've made great friendships with you both, and I also like to say you've given me opportunities that I wouldn't have imagined during this process, so I'm thankful for your impact on my career. Pete Pokran is the glue that holds AOS together, and that is an understatement, but a lot of what I have done, specifically Weather Watch, and also getting all this data, would not have been possible without him, so thank you for that. The office staff have helped me get to this point, answering all my logistical questions and also being great friends. I have to thank my Martonians, Libby, Poach, and Flora. I love you guys, and you made coming to work so great, and I'm going to miss you. I'd like to thank my mom, dad, my sister. They gave me life. They're the reason I'm literally here today. But they are also, I wouldn't have guessed that this could have been possible without their love and support throughout my life, so thank you so much. I know they're watching online. I have many family and friends. A lot of you, I see you today and are watching online. Thank you all so much for getting me to this point. And like I put in my dissertation, it takes a village, and I'm glad you were all part of my village. Finally, of course, I have to thank my dog, Calvin, who's right there, who has no idea what is going on. He's sleeping right now. But I'm thankful for him, and it was nice to go home and see him every day. So with that, I'll conclude. Part of these results are in a publication that should be going out in a week or two, hopefully. The second part is part of a paper under construction, and then I'll take any questions. Thank you.
Questions for Patrick?
Could you go to slide 62? And the 500 relative vorticity in the storm region, is there a reason there's that couplet, or is that just a fragment of the method?
That's a great question. There is actually a storm sitting here, a previous cyclone at this time. So I think it's picking up on the couplet with that storm. Yeah. It's a much weaker storm than this one, but there was one sitting there. Good question.
It's taken me a long time, Grant, to understand that that box doesn't, what's in that box doesn't have anything to do with the diagnostic. Is that
Yes,
right?
that's
the
right.
box is
Yeah.
just a geographic mark.
Right.
So you're looking at the upstream thing. That thing is related to another upper front that's across the back. Yeah.
Yeah, so that is actually saying 24 hours later, if you increase vorticity just right there, you would increase the strength of the storm for whatever reason. Yeah.
Really, really interesting talk, Patrick, and I'm going to throw an ocean question in this talk, is that 2019 was also a really big marine heat wave right in that region, and I'm wondering how that could have affected the intensity or the storm track being equatorward, or just feeding into the storm.
Yes, let me pull up. I have a plot for you.
Of course.
Okay, it looks like it didn't upload, which is always a fun time. But so what I'll say for answering that question is I'll pull up this spot right here. We looked at the influence of sea surface heat fluxes from the Air 5 model from this development, and it actually turns out during its entire life cycle they were lower than normal for this storm, which doesn't necessarily mean there wasn't an influence of the marine heat wave over this region, but it just says they were lower than normal heat fluxes. What I think is more confounding is if you set up a marine heat wave over this region, persistent, and I know it was largely in the upper ocean, you're going to have a lot of just ambient heat flux going on throughout much of the fall that this occurred. You can then raise the thicknesses because you're just constantly adding heat to the atmosphere, which encourages the development of this anticyclone, but specifically it also could have just raised the ambient temperatures over this region, persistent, and then you have, in late November, you have a colder region of air, and forcing, then you have the combination between the colder wave from Alaska and just this ambient, very warm conditions compared to normal. And I think what it did is it set up this baroclinic zone, or encouraged its development, made it more robust than it otherwise would have been, because this is what we were really focusing on, is it was that baroclinic zone, and then the flow from the anticyclone and the cyclone to result in the rapid cyclogenesis. So it wasn't particularly the heat flux.
Yeah.
We saw that the PV surface was largely zero, but it did set up these conditions to result in the cyclogenesis. Yeah. It's a great question. It's something I've considered for a while. Yeah.
I'm glad that you've thought about this. Relatedly, for the diabatic Rossby wave, so that it needs moisture, and if you have a warmer surface, you would be able to get more moisture into the atmosphere. So I was wondering if there's a relationship between the strength of that lower level wave and the surface temperature, and if you'd be able to get stronger waves with warmer temperatures or in a warmer climate.
Yeah, absolutely. That is sort of the idea, is if you increase that, specifically the heat flux, not necessarily the heat at the center of the storm, but you have really strong heat flux, more theta E flux into this development region, you're absolutely going to set up a stronger diabatic generation and PV generation in the storm.
That's really cool with your two parts of the storm that seem like they don't interact for a long time, is if you can say that, like, the lower part of the storm is being strongly affected by this, the upper part of the storm maybe would have done the same thing either way, but
Correct.
At the end you have something stronger, at least partially because of what's going on. So
Exactly.
yeah.
Yep, that's exactly right. Yep.
Cool.
Yeah.
Yeah, no, excellent presentation and diagnosis. I was curious about your PV partitioning. When you did the partition, one of the results that you showed was that it seemed that it was the upper tropospheric winds and upper tropospheric temperatures associated, or those winds associated with the upper PV,
Yes.
temperatures associated with the PV that led to the development of the upper front.
Yes.
How, if you could go back to how that partitioning was done, how sensitive, I know things added up, but did you have the same volume, or were you effectively looking at the same pieces of the atmosphere from one partition time to the next? When you say upper tropospheric PV, that's everything above.
It's everything 650 and above to 150 with relatively dry, relative humidity. Yeah.
So if you were to break that, I'm just trying to understand, what does it mean for things to develop just using in terms of the upper troposphere. If you broke up that upper piece, could you actually have interactions between the lower part of the upper piece and the upper piece
I
itself?
see what you're saying. You definitely could. I think because it was primarily driven by the lower level wave, I don't know if that would be particularly sensitive to partitioning this upper tropospheric piece into maybe more tropopause undulation versus just in between. But it would be interesting to do. Yeah.
Right, so how do you understand, how do you explain just the development that you saw in the upper troposphere being solely driven by fluids on the upper troposphere? Is that understood? Well,
Yes, there. Yes. In this case here, a lot of this subduction of the tropopause, a lot of this subduction was done primarily due to maybe CBA or cold advection along the jet. Nothing really that did a lot of this upper level development, the upper level wave, was anything in this ambient region here. It was largely due to the upper level jet and subduction through that jet core. If that's answering your question. I don't know if it'd be too sensitive. It'd be something you could easily do, but a lot of it was done by processes along the jet and along the tropopause in this case.
Okay. Yeah, if I could just follow up on that. We've got all the different species of omega calculated for all of these interaction terms as well. We just show you the total omega here, because it's
Yes.
the simplest way to see the picture. So you might be able to get more insight about exactly your question by looking at, shear-wise omega, the across isotrope omega, all
Yeah.
that kind of stuff. We have them all for each of these 16 species. But it gets to be, if the magnitudes are small, because everything has to add up to the total. So the more you partition it, the smaller the signal in each piece.
That's right. Yeah.
I have two questions. The first being, when you do the piecewise, where you showed the progression of the deepening relative to the particular piecewise function that you are investigating, and you mainly focus on the upper troposphere as well as the inner portion. And then you noted that for the surface, there's an initial an initial deepening, and then it goes to a near zero response. This is probably more so a clarification question. Is that anticipated, and what is the, do you have an explanation as to why it goes to near zero for the rest of the deepening portion?
Yeah, that's a great question. I think it's related to the looking at surface heat fluxes in this case. So this would represent near surface thermal anomalies, which are like near surface PV anomalies. Initially, we did have a region of locally stronger baroclinicity near the surface, but throughout the development, we saw that there was little connection between that near surface PV, all those heat fluxes regenerating, warming, continually warming the lower troposphere, which fits into when we tracked the sea surface heat fluxes for this event. We saw that they were largely lower than normal, and so it seems like it was just that initial setup. Initially, we had a lower level wave spawn, and then the diabatic heating just took off and sort of completely dominated cyclogenesis. We're also over a region where the water is generally cooler than other rapid cyclogenesis events, so that might also be, this might be sort of expected where we don't see, especially later on, where we're into the colder waters. We shouldn't really see any contribution from the lower near surface PV, but this this initial PV dominance into near zero is definitely different than other cases of cyclogenesis. Yeah.
And then my second question is kind of taking a step back. In terms of impacts, do you have a thought as to the proximity of the deepening relative to the coastline, and how does that result in impacts? Because I know you looked at this through an ensemble lens as well. I'm wondering if you looked at the results of the deepening, the location.
Yeah, absolutely. So this, let me show. I'll show this animation. So this did underwent its maximum deepening. Okay. It underwent its maximum deepening right off the California coast. And so it's reaching its strongest peak as it's making landfall. Particularly this case of cyclogenesis occurred right before Thanksgiving. And so there were a lot of flight. This did reach its maximum peak right near the coast. Compared to other events of cyclogenesis, like the November 2024 one, that storm actually, let's go forward. This one. So on the left here are the impacts of the November 2019 case, the one we just looked at. There were travel disruptions, Thanksgiving, classes canceled all the way to Minnesota from this event. But this case in 2024, this storm didn't even make landfall until weeks later after reaching peak intensity, and it still resulted in more than 1 million, close to 1 million customers, which might be over 1 million people without power, and it also resulted in a fatality. And so even though this storm specifically wasn't as strong as this, the one in 2024, because it reached peak intensity and then made landfall right afterwards, absolutely had a lot of impacts. Yeah, especially when you compare it to a storm that didn't make landfall when it reached peak intensity, still had a lot of impacts. So it's sort of like timing and proximity to population centers. Yeah.
One of the things that you said was unusual about this was the equatorward motion. I was just wondering, through different aspects of your analysis, what came out as being the primary drivers of that part of it?
Great question. I will show. Let me step through, go back to the synoptic overview. Diabatic cross waves are driven by this lower level frontogenesis, as I hinted on. And so you'll see if we just track where this lower level frontogenesis is, it's directly to the east at this point. Now step 12 hours ahead. It's again directly to the east, maybe slightly to the southwest. Or southeast, excuse me. Just go forward again. Now we have it situated most notably to the southeast. Going, even though it's interacting with the mountains, it's also to the southeast. So because this was largely driven by that diabatic cross wave aspect, the lower level frontogenesis is going to dictate where it moves. And because it was disoriented such in a way that it is always either to the east or the southeast, the storm moves southeastward in this case. And the real influence of the upper level wave came through almost too late to sort of move it forward. It was always driven by that lower level piece for much of its development. Yeah.
Well, except that the upper front comes in from the northwest.
It does, yeah.
And so it actually raises the question to me of how many explosively deepening cyclones in the Gulf of Alaska are influenced by upper level jet front systems. Probably not many, because they don't develop in the southwesterly flow, as Andrea and I showed like 100 years ago. So they don't.
Not that old.
But so there's a whole bunch, there's a whole collection of really intriguing questions that this study's introduced. That thing there is driving some of the southward motion at the middle stage of development.
Yeah, right.
Because if you go 6 hours earlier, you're exactly right. It's all the diabatic Rossby wave, because that upper level vortex is simply really weak PBA north of the low. And you've got a zonally oriented baroclinic zone along which the frontogenesis is driving it to the east. It's just going straight to the east, and then when that thing gets going, it drives it southward. Is maybe another way to look at that.
Yeah, absolutely.
Given the prevalence of the surface characteristics, did the impact along the west coast, because there's a bunch of high terrain there, did the impact of its interaction with that high terrain have anything to do with all of that?
No, it seemed like, so a lot of these cyclogenesis events happen well in the ocean, or they're on the eastern side, like the continents to the east. Whereas this storm, it seemed like it just strengthened and strengthened and strengthened, and suddenly when it made landfall, hit mountains, and then that kind of eviscerated the storm. Specifically, it didn't seem to care that where it was, and like we've shown, here's an anticyclone, it just moved completely through it and still deepened rapidly without really caring that it was there. So there's a lot of weird and unusual factors of this. That one being, it just continued to deepen until there was no more low-level baroclinicity for the working. Yeah.
It makes me think, Patrick, I'm sorry, just
No, that's
make a quick comment. all the time we spent thinking about this storm, and it never occurred to me at any point along that, how did this thing cut through an anticyclone? It had to have been driven by something in the boundary layer. And
Yeah,
it never
yeah.
occurred to me.
Yeah,
And then so you did your analysis, and then it proves that it didn't, so.
really strong low level diabatic heating, yep.
Yeah, sorry, I interrupted.
Yeah, Gerald?
Is there something unique about the North Pacific that allowed this unusual case to happen, or do you think this could happen in the Atlantic Ocean as well?
This could happen, theoretically, I think it could happen in the Atlantic. What's been going on for this specific case, I don't know particularly about the November 2024 one, but you have Alaska, so Alaska's a cold air mass. Essentially, it's a refrigerator, and when you get waves that move through, they bring a lot of cold air towards the Northeast Pacific Ocean. And if you have those warmer than usual, that Pacific blob, the heat wave that was sitting there, then you have increased baroclinicity, and those things can work together and then result in a stronger cyclone. So you do need somewhere where you have the interaction between a cold air mass and a warmer air mass. Undoubtedly, that can happen over the Atlantic. It's just, this seems to be a preferred region, is actually highlighted as a preferred region for rapid cyclogenesis, exactly where the storm formed, because you have Alaska and you have relatively warm tropical air to the south.
Any other questions for Patrick? Okay, well, join me again in thanking him for any. Now I think we'll dismiss the general audience, and then just the committee will stay to, with the fear of God and Patrick.